about this question, and I'm glad somebody brought it up because it's going to show up a couple times. We have a spring, and my understanding about this problem is that the spring is not on the section of the ground where the friction is, or it is. I can't remember, and it doesn't matter. I'm going to talk about it both ways. So let's talk about a problem where the spring is not on the section of ground where the friction is, and then we'll just slide it over so that it is. Is that okay? Doesn't change the problem dramatically. As a conservation of energy problem goes, now this is in the work energy section of the book, but as a conservation of energy problem goes, we can address this problem by pulling back the mass against the spring. This will be storing energy in the form of 1/2 kx squared. And they give us a spring constant and all that kind of stuff. And then we release the box from rest, so that means this is the only energy the box has, and it's going to be pushed by the spring until it leaves the spring and now has some amount of kinetic energy. Since the system is on horizontal surface or on horizontal ground, we can probably state that unless there is something to take energy away from the system, we can set this equal to 1/2 mv squared. This will tell us how fast it's going. However, it's going to reach this point where it's going to go into an area where it's going to be losing energy. Right? So this is what I really want to talk about, going from A to B, where the box will be here. And during the time that it's here, it will be experiencing a force that does work on the box, because there are 3 forces acting on the box during this time. And eventually the box will make it to here, where it may or may not have kinetic energy still. It's on level ground though, so there's the possibility that when it makes it all the way to B, let me make sure it makes it all the way there, it may or may not have kinetic energy 1/2 mvb squared, and I'll put VA squared there. Everybody good so far? Following this? This is in the work energy section of the problem, or of the chapter. So being that it's in the work energy section, I would have argued last week, well, week 4 last, the work is equal to the change in kinetic energy of the box. And I would have suggested we find out how much work was done while the box is moving across the area where there is friction. Now, I'm assuming that the box acquired kinetic energy from the spring. And I'm still going to make that assumption. Now, during this, I would find that the work done is going to be, force times distance times the cosine of the angle. And this is going to be K at point B minus K at point A. Right? Kinetic energy at B minus kinetic energy at A. That's what the delta means. Now this, whatever this is, I'd have to work out and figure out how much work was done. If positive work was done, I expected the box would be speeding up. I'm pretty sure we can all agree that negative work is going to be done by friction, and therefore the box is going to be slowed down. Does that seem reasonable? Now, this part, there's no way around this. If you're going to calculate work using a force, you're going to have to find out the size of that force, the distance that that force acts, and the angle between that force and the displacement. You'll need that if you're going to calculate for the work done directly from a force. You can always calculate that work by looking at the change in kinetic energy, but they're giving us, they're not telling us what the final kinetic energy is. So we have to find that work here in order to determine what the final kinetic energy is. This means that we have to come up with an expression for the frictional force. And by now, I know it's a lot of substitution, but I'm really hoping that it doesn't take you a whole lot of brain oomph to kind of put in that's going to be mu mg. I mean, some of these things they happen the same way every time. So something on level ground experiencing friction, well, the frictional force is going to be proportional to the normal force, which is directly proportional to mg. Now, times d times, well, this is going to be -1. So this tells me that the object loses energy. Good so far? Questions about this yet? Well, we're moving into a section about conservation of energy. And whether you like it or not, there's more than one way for us to approach these problems, especially considering that these problems can have little twists in them that make them appear more difficult than they are. So let me first start out by saying this whole statement here, although not a big deal, can be reworded. Because what I want you to consider is the object was on level ground, so never did the object's potential energy change. It's gravitational potential energy. So I could write this as Ka plus mu mgd times -1 equals Kb. I just moved the negative Ka to the other side. And I'm going to take this, and I want you to think about it. This is the work done on the box. If we were looking at this from the standpoint of conservation of energy, I could be breaking this problem into state 1 and state 2. And you'd be asked to figure out which of the kinds of energies are occurring at state 1 and compare them with the types of energies occurring at state 2 and ask yourself if they're equal. Well, what if they're not equal? This is a case where they're not going to be equal. And even though I can wipe these off, that doesn't help very much. I think all of you realize that that's got to be true. From a standpoint of conservation of energy, what do we do now? Do we say we can't solve this with conservation of energy? That's one method. We could dive back into the last chapter and talk about all the work acting on the object. Or we can have another way of considering how we can make these things equal. Now, I'm going to pause here and tell you that I've been doing this for 26 years. And in 26 years, the flavor of how I'm supposed to explain this to you has changed a number of times. You guys who are in AP Physics 1 might remember that the Actina book would really like it if you did little bar charts, which I thought were just utterly ridiculous. Like this, though, where the equal sign appeared where the weight is, and that you're supposed to have bar charts. Like this thing started with all elastic potential energy way over here, and then eventually has some kinetic energy way over here. And that somewhere in here, something did work, but it was negative. And that sits on the equal sign between the before part and the after part. That's how the Actina book, the one that's for AP Physics 1, wants me to do this with little bar charts. I can't stand the little bar charts. But you might like the little bar charts. If you do, I'll check you out an Actina book, and you can read all about it. There's even these bar charts in your book, but they don't spend as much time with them. One year, for a while, it was popular to put work done by friction or work done external to the system right on top of the equal sign and decide whether you're supposed to add it or subtract it as if you're going over the equal sign and doing work. I didn't particularly like this couple of years either. I'm going to tell you how I feel about this. And let's see what you guys think. I am a pragmatist. The object had this amount of kinetic energy at point A. The object has this amount of kinetic energy at point B. However, we know they're not equal, but there's energy still in the system. The energy came from the motion of the block across the rough section of the surface. That means there is heat in the surface, which doesn't exist until after the object goes all the way across the rough patch. So I like to say that, you add the amount of energy equivalent to how much work was done by friction. That way, you are accounting for all the energy. Which is important to me. I like the idea of this as an accounting thing. We have so much energy. Where did it go? There are several advantages to thinking of it this way. The first advantage is that your works or your values are always positive. Every value for energy is always positive in this conservation of energy equation. The other thing I like about it is that it allows you to see very discreetly all the different places where the energy could go. Now, this problem is not particularly hard. And so picking any one of these, you'll realize it's not really that hard to deal with. But it also allows us to consider this, a slight modification on this problem, where the rough patch might exist along the entire track. If I can grab onto that, I'd appreciate it. There. So it's rough all along the track, so that when we started with the box here, it was experiencing friction the moment that the box was in contact with the ground. Now, the reason I kind of like using the method I'm talking about here in this circumstance is because under these circumstances, I can still look at the cases of the problem. And I can state that this is state 1 of the problem, and over here is state 2 of the problem. In state 1 of the problem, there was elastic potential energy. In state 2 of the problem, if the box is moving, and it's a big if, but I'm going to assume the box is still moving when I'm done, it has kinetic energy, but also by the time it reaches state 2, it has left energy along the ground. This allows me to deal with not only this part of the surface where it drifted, but also the part of the surface where it was in contact with the spring. I don't have to worry about the fact that the spring's force on it was changing the whole time. I don't have to deal with that at all. All I have to do is realize that the work done by friction takes place along this whole surface while it was moving. So I have energy here, and energy here, and I never have to deal with the fact that during the time when it was in contact with the spring, the net force on it was something that was always changing the whole time. That's kind of why I like this method. The other reason I like this method is because it allows. So in this problem, which of course is similar to what we just saw, the difference is the patch that has friction is also at an angle. One advantage of considering what I just did is that, well, I can consider the fact that the box is going to eventually make it to here. When it makes it to here, we're told it has kinetic energy because it does one of these. Right? Problem number 73. Well, how do you want to deal with this problem? If we go back to chapter 9, you have to find the work done by friction while it's here. You have to find the work done by gravity while it's here. And this total work will equal the change in kinetic energy. You could do it this way. Nothing wrong with it, but it's pretty laborious. And it requires you to remember all of the forces acting on the box as it goes up that ramp. Or it also requires that you figure out how fast it's going just before it hits the ramp. Or you could consider what I just talked about. I see 2 states of the problem. State 1 here, state 2 here. At state 1, I see only elastic potential energy. At state 2, I see gravitational potential energy because I am above the reference level. I think I have kinetic energy because the object is going to jump off the ground. Seems like it probably has some. But I also know there had to be some heat given to the ramp, the work done by friction. Now, is this really any different than writing out the works and doing the total work? No, because the work done by gravity, by definition, is the change in potential energy. That's where this term comes from. So it's still all the same. It's just a different way of thinking about it. Find the way that satisfies your sensibilities. None of these are wrong. I tend to like this. It feels very elegant. More importantly, everything is positive. I never have to worry about making something specifically negative. It's all about where the energy is and accounting for the energy. The box had this much at state one, and the box and the rest of the system must have all of that energy somewhere. Now, to be perfectly honest, I'm blazing through the parts of this that are hard, meaning this one's not MGH, no problem. You can figure out how high it is. 1/2 kx squared, that shouldn't be a problem. You guys can do that. 1/2 mv squared, still not a problem. I mean, come on, the work done by friction. There's no way around the fact that I have to find out that a frictional force equals mu mg cosine theta. You're going to have to do that. You may not have this memorized yet, but I don't know what you're waiting for. A box on a ramp experiences this much friction. It's getting to a point where I sound like a broken record, just like the component of the force down the ramp is mg sine theta. Yeah, it sure is. If you can't jump right to this, it's okay. That just means that you have to do the force problem. That's okay with me if you want to do it that way. Break this up into its components. Show that normal force equals mg cosine theta. Remind yourself that friction equals mu mg cosine, or maybe just commit this to memory. That's a pretty quick way. If it's a pretty standard ramp, that's the frictional force from the ramp. Look, I think I've asked you to memorize 5 things. It's not like a foreign language where the entire thing is in another language. I'm saying just memorize 5 things. And mg sine theta, mg cosine theta, that's one of them. Now, I don't really know whether I answered your question or not. I said the things that I wanted to say. Did I answer what you needed in order to be able to solve the problem from chapter 9? Okay. Then that's good. Good news. Yay me. If you actually have started this problem, you realize that the question really is about where this thing lands. And so all of this was to be able to just get how fast it's traveling here. And then you weren't even done yet. I'm going to remind you that there's something else I suggested you memorize. Of the 5 things, this is one of them. Might be a way of making that part of the problem go a little bit faster. Right? The range equation, it takes off from this height, lands at the same height. If you can figure out V, this would go pretty fast. If you can't, then you're stuck with this. And who wants to do that? I made you do that earlier in the homework with the ski jump problem. That was no fun. The one where it comes off the ski jump with a delta Y of 3 meters. And sound familiar to you? Hope so. All right. All right, so what's the next one you want me to do? What was in order? Where do I go next? Okay. So in this problem, the ice cube is just going around in this circle, I guess indefinitely, assuming that it doesn't lose contact with the top up here. It's going to do this forever because it's not losing any energy. So they would like you to figure out the velocity up here. I see 2 states of this problem, state 1 and state 2. But if you didn't understand that the pipe is horizontal, but the ice cube is going vertically, I can understand how the wording of the problem without a picture could have been troubling. So the ice cube is going in a vertical circle inside a horizontal pipe. Does that make sense? If not, I'll make sure we draw a picture next time. But I'm thinking gravitational and kinetic up there at the top, wouldn't you? And kinetic down there at the bottom. So mg times 2r plus 1/2 mv squared at the top, and 1/2 mv squared at the bottom, and just set these equal to each other. Does that seem all right? If it were me, I would be able to answer this next question. Because if this was question A, question B from me would be what would be the normal force on the piece of ice at the top of the pipe? That's what I would immediately ask, say on a quiz tomorrow. That seems like a very reasonable question to me. And if it's not a reasonable question to you, let me first ask, is there any trouble with what I just did here as a conservation of energy problem? We feel pretty confident? So the second part of this is to recognize that at the top, the object can only be traveling in a circle if there's an unbalanced force towards the center. And I perceive that there are two forces acting on the ice cube at the top, and both of those forces are pointed towards the center. Now, those two forces have to equal MAC. They have to cause centripetal acceleration. So I would argue that now that you know the velocity, you could probably come up with an expression for the normal force as well. And let me point out something, because I'm often interested in helping you save time. In this problem, you reach a point where you solve for mv squared. You see that, right? 1/2 mv squared. And over here, you're going to use mv squared. Sometimes it's not in your best interest to go all the way and solve for v. Sometimes it might be in your best interest to leave it in terms of mv squared, especially if you're going to reuse that. FRQs, you're limited by time, so anything you can do to save time, I think, is helpful. So if I was to ask a part B of the question, this is what I would ask. But you would need the mass of the ice cube, and I don't think they give it. But tomorrow, I'd probably give whatever it is. And whether it's this thing going in a vertical, tube, or you have an object on a string that you swing around, it's the same question, except that rather than normal force, the object on the string would have tension. So I'm bringing that up because you have another problem with tension in it. Correct? The pendulum question. All right. I didn't record, and I wanted to. The kid starts at the top, slides around to the side. They are always one radius from the center of this circle. But I think it's pretty fair to say that at this moment, they are lower than they were. Would you agree with that statement? Okay, good. Hold on to that for just a minute. They have a potential energy at, let's say, at location 1 of mgr. Now, at location 2, their gravitational potential energy is not based directly on r, but is based on whatever this height is. Does that make sense? The problem is they want me to use this angle in the problem to determine what this height is. But I think that's okay, because whatever this height is, couldn't I just draw a similar line over to here, make a right triangle, and wouldn't this also have to be h? You guys okay with that? You guys see what I'm doing? So I need the height above the ground. So I'm just using a little bit of the old trigonometry and geometry to tell me that this h has got to be r cosine theta. It's the adjacent side of the triangle defined by the right angle and r. We all good? All right. So that means this is r cosine theta. get all this out the way because I don't need it. All right. So now their gravitational potential energy has got to be mgr cosine theta. And they have kinetic energy equal to just 1/2 mv squared. Good so far? Seems to me, if there's no losses to the environment, I can say that mgr has to equal mgr cosine theta plus 1/2 mv squared. How are we doing? Can you solve that for v? Good, good. Because this problem isn't about this. They would like to know when the kid is no longer traveling on the slide and has turned into a projectile. Because if you look closely, you'll notice that they have to have a velocity that is this way. They are traveling along the edge. The only way they can travel in a circle is if there's an unbalanced force towards the center. Let's consider all the forces acting on them real quick, because I can only think of two. mg and normal. Correct? Now, part of mg is making them go faster. We know that. That's why their kinetic energy keeps changing. But part of mg is keeping them attached to the ice. Right? It's pointing towards the center, so they travel in a circular path. I'm going to make my coordinate system this way. And if you look at my picture, notice that h is straight down. That means this is theta. So this is theta. More importantly, this is mg cosine theta. Now, I understand people have to leave, and I'm not going to stop you, but I'm going to finish. Mg cosine theta minus the normal force has to equal MAC. If there's not an unbalanced force towards the center, they don't get to stay in the circle. When do they leave the circle? When they're no longer in contact with the circle, they have left the circle. Mg cosine theta has to equal mv squared over r. This is a tough question. I love this question though. And this moment where we are right now has just turned into algebra, because you have this relationship that has v in it and this relationship that has v in it. If you eliminate v, you'll get the angle where they leave the ice. And I mean, you'll get an angle like a number of degrees away from the center where they leave the ice and have changed from a person on a slide having a fun day to a projectile about to face plant on the ice. I will finish this once the room is quiet again, so you can walk through it if you wish. All right, so what you need to do now is set these two equal to each other. What I'm going to do is a little different. I'm going to multiply both sides of this relationship by r and get mg cosine theta equals mv squared. And I'm going to multiply both sides of this equation by 2 after I move this over to the other side. So when I move it over to the other side, I get mgr minus mgr cosine theta equals 1/2 mv squared. And now I multiply both sides by 2. And that gives me 2 times all of that. So now I have mv squared here, mv squared here. I can set these two things equal to each other. Okay. So let's do that. And this is getting messier and messier. So yeah. I would prefer it to be less messy. So let's put it way over there in the corner. And we have, you grab that. 2 times mgr minus mgr cosine theta equals r mg cosine theta. All right, so if you look closely, every term has an mgr in it.
Yeah.
So mgr, mgr, mgr. So I get 2 minus 2 cosine theta equals cosine theta.
Yeah. Okay.
Move the 2/3, move to the other side, I get 2 equals 3 cosine theta. So cosine theta equals 2/3. You certainly get an angle. And I don't remember what the angle is, but let's take a look. So I got to take the inverse cosine of 2/3, and I get 48 degrees. So kid leaves the ice when that angle equals 48 degrees.
Okay. I got it right. I go put it in the calculator because I didn't.